Kirkland, and welcome to Beyond the Gates. This season, we're going to be highlighting ERDC's legacy of groundbreaking research and cutting-edge technologies. Join us as we explore how innovation continues to drive progress in military and civil works missions. I am delighted to have with me Dr. April Bowman. She is a research civil engineer with the Geotechnical and Structure Laboratory, otherwise known as GSL, and we're going to be talking about spinning science inside the ERDC Centrifuge. Good morning.
Good morning. It's so great to be here with you.
I am so glad you're here because, wow, I've seen the centrifuge and it's cool.
It's big.
It's big and cool.
It's fun. Yep.
So we're going to dive into a lot of information about the centrifuge, but what we're first going to talk about is tell me about yourself and your background.
All right. Well, I started as an engineer in the United States Air Force, so
that's brand new information. Did not know that.
Did not know that? Yeah.
Yes.
I got my degree in aerospace engineering from Boston University, and then I was in the United States Air Force for 12 years. Following that, as an active duty officer, I served all over the world in the civil engineering career field, including Guam, overseas in the Middle East, of course, England, Korea. Really enjoyed my time. Loved that role. And then while I was in England, I had gotten a master's degree in structural engineer kind of during my time in the Air Force, and I got picked up to be a runway pavements inspector. And when you get picked up for that, you have to go and get another degree. And because I was in England and I was actually very close to Cambridge University, I went and got a master's in geotech engineering at Cambridge University.
That's fantastic.
Yeah.
That's very cool.
But while I was there, I was presented with the opportunity to get a PhD in geotech engineering, and I took the opportunity. So at that point, I jumped to the Air Force Reserves. I'm still an Air Force reservist. And I got my PhD in geotech engineering. Now, Cambridge has one of probably the most productive centrifuges in the world. And so that's how I got the centrifuge stink on me, per se.
I like that expression.
Yeah.
That's cool. Okay.
So really enjoyed my time there with them. And then I moved on to Nottingham, where I was a postdoctoral research for them at their centrifuge. And then I moved back to the States, and I was another postdoctoral researcher at the Colorado University at Boulder, and they also have a centrifuge. And that's when I moved to ERDC and took over this centrifuge.
Okay, so your passion is true.
I love it. It's fun. It's fun to spin things around really fast. So I want to tell this story. When I was at Cambridge, I was, we all get a little cubicle at Cambridge, and for 5 years there was a picture on the wall of the ERDC centrifuge right at my back at my desk.
So it's like a subconscious thing. You knew where you were going before you went.
I think it was one of the original publicity photos of the centrifuge from when it was commissioned in 1995. The connection there is our centrifuge obviously was helped designed by a lot of the old professors at Cambridge, notably Dr. Andrew Schofield. The Centrifuge Research Center at Cambridge is called the Schofield Center, just to give you a sense of how prolific this gentleman was in centrifuge research. He is still alive. He was alive at the time I was at Cambridge and quite active. He would come by the Schofield Center quite a bit. And when he found out that I was associated with the military and that I was getting into centrifuge research, he would stop and talk to me and tell me these stories of him building the ERDC centrifuge and working with Scott Steedman and Richard Ledbetter, all these people who were really instrumental in getting the ERDC centrifuge off the ground. And he would tell me these stories. Do you know them? And I'm like, well, I'm kind of young. I don't know them. But he would tell me these stories and the stories of the very first time it ever spun up and the stories of how it got delivered from the New Orleans port and it had to be unpacked because it couldn't travel by truck. It was too big. The stories of the wrong metal was used in the arms to begin with, and we didn't know that. It was a manufacturer, not from Actidine, but in Germany, they put the wrong metal in and they stretched in the very first time we spun it up to 300 G. He told me that story many times. And I've heard that story now from ERDC folks who are here around as well. But anyway, at the time, I never would have guessed that eventually this centrifuge would be my baby, my life.
Your being.
Yeah. And so it's kind of fortuitous that I got all those years to spend with Andrew Schofield and hear those stories, because now I have a fondness for this centrifuge in particular that really started there at Cambridge and grew with those connections.
That's an awesome story.
Yeah.
Well, okay, so then we're going to go into what is your role at ERDC?
So at ERDC, I am the research civil engineer over the ERDC centrifuge. So
there's just one.
There's only one.
Okay.
There's only one. It's big. I guess I can get into talking about it. The ERDC centrifuge was built in 1995. It is a beam centrifuge. So why that is unique? So why do we have a beam centrifuge? There's lots of centrifuges all over the world. You're going to, I think probably what most people think about when they think about centrifuges is either what they see in the movies, so astronauts and pilots going into a centrifuge and getting G-loaded and feeling G-lock and passing out about 9 to 10 Gs, and then they slow down and they come out of it, and it's how they train for what they feel in a jet, in a high-speed jet. So there are those centrifuges. Ours is a little different. Ours is a bit more robust. And the reason being is because we test very heavy models in our centrifuge. And so that is, that's what it does. I think everyone's felt a centrifuge force, what we call centrifugal force or acceleration on your body. If you think about when you go to a Ferris or you go to a state fair.
Right.
And there's a spinning ride of some sort, the teacups or something along those lines. You feel that force on your body pushing you against the wall.
I don't like that force.
No, a lot of people don't. But that's it's a very gentle force. You're probably talking half a G, maybe 1 G. You feel it in a roller coaster. So let's talk about our centrifuge. Our centrifuge goes up to 350 Gs. Yeah. And just to, go back to that pilot, again, that pilot passes out around 9 to 10 Gs. So when you start thinking, my centrifuge doesn't even really get started until about 10 Gs. So we don't offer rides on our centrifuge.
Good
it's a
to
little
know.
bit different.
Okay, so that's, again, your role is pretty much with the centrifuge, right?
Is.
And then we got into what exactly it is and what it does. Is there anything else that we need to know what it does?
So we handle very big models. It's just a very big centrifuge. We build models of all sorts of civil infrastructure, civil structural infrastructure. We'll put it on the centrifuge, and the whole goal is to put that model under the same stress that it would feel in real life if it was scaled up to its true size.
Right.
And so we have a lot of very productive, if you look at centrifuges around the world, very productive research output. Because it's controllable, we can repeat the experiments, we can make minor adjustments to the experiments, and it gives us a wealth of data to go and then put into numerical modeling or compare with real-world infrastructure.
Right. So what makes the ERDC centrifuge different or special from others across the world?
So the ERDC centrifuge is a geotechnical beam centrifuge. Now, it's not because we only do geotechnical work, but that's just its title. There are about 110 of those worldwide in the same size category.
Really?
Yep, same size category as ours. There's only 4 in the United States, and we're one of them. Why is ours special? Ours is special because of its speed and load capacity. It can handle up to, like I said, 350 Gs. 350 Gs on our centrifuge is about 370 miles per hour, just to give you a sense of how fast the centrifuge can go. And then couple that with its load capacity. We can carry anywhere from 0 to 8 tons on our platform. So those two things together give us our performance envelope, and it's incredibly large. In fact, it's the second most powerful centrifuge in the world. That's what makes it special. I think the other thing that makes it special was in 1995 when the original designers of the centrifuge came up with the concept for this centrifuge. There weren't very many at that point, and we were working with a company called Accudyne in France, and we were also working with Cambridge University. That's that connection again. They built this centrifuge with the U.S. Army's research mission in mind. One of the big things we do is looking at blast mitigation, blast protection capabilities. And there's always the risk when you have a blast on the centrifuge platform that something gets blown off the platform, not the platform itself, but out of the model onto the floor while the centrifuge is spinning. The centrifuge is essentially a seesaw. It's balanced very carefully. We can't be more than about 100 kilograms out of balance. If something were to fall off that platform, or if we're doing a water experiment and the water comes off the platform, this centrifuge has the ability to rebalance itself in flight. That's one of the first centrifuges that ever had that capability, and the reason we have it is because of the Army mission and the types of testing that they wanted to do at that time.
Right.
So I think that it's special because, one, yes, its size and load capability is, of course, huge, and that always makes it fun.
Right.
But also because from the get-go, the designers really kept in mind what the research mission of this centrifuge would be.
I knew this show would be interesting, but I'm just so intrigued. So what are some of the current projects or experiments that use the centrifuge?
The one I want to really talk about, and it kind of goes back to our history in the centrifuge. Following Katrina, obviously very devastating for New Orleans, one of the major failures that happened after Hurricane Katrina was the eye wall failures. It wasn't the hurricane itself, it was the water loading on the eye walls that pushed the eye walls, either moved the eye walls out of the way, rotated the eye walls. Essentially, the eye walls failed, and then that's where we saw the devastating flooding across New Orleans. We were the centrifuge that we actually took soil from New Orleans, brought it up to ERDC here in Vicksburg, and recreated the loading on those eye walls in the centrifuge. We built the model, put the eye wall in, and loaded the water, brought it back down under G loading, and watched, because we weren't really sure how those walls had failed. There's just been so little evidence and testing on the walls to understand their failure mechanisms that no one really understood why this devastation had happened.
Right.
And the centrifuge was really instrumental in looking at why those walls failed, what were the failure mechanisms, what were the things that led to the failures, and how could we correct them as USACE and as ERDC. So we did some of that work after Katrina, which I think was in 2005. Now, we did that with their soil, with the New Orleans soil, but we never really went back and looked at, well, what about sands? What about over-consolidated clays, normally consolidated clays? And out there's still 10% of levee systems in the USACE portfolio is eye walls. And, there's a real reticence about, well, are these safe? What happens if we load these like this again? 70 existing eye wall systems are still in New Orleans.
70?
70,
Okay.
yeah. They're in NOLA. So we are going back right now. That's one of the projects we're working on, is looking at how does the influence of the levee geometry, the embedment depth of the wall, the soil profile, wall stiffness, loading, unloading, how is all that affecting those eye walls, so that when we go out to inspect the eye walls, when we look at risk of what is the flooding potential around this eye wall, we can say, well, is this a system that needs to be replaced or not? And then we're coupling that with a lot of the numerical modeling that's going on. There's a great group out there doing that. So we partner with them to show them our data. They come up with more data. Together, we're able to give USACE a better answer on, okay, is this eye wall in this location safe or not?
Right.
And so that's a project that's going right now. It's in partnership with the Department of Homeland Security, working with the districts down there. Outstanding and incredible project. It's been a lot of fun to be part of.
It sounds like you stay really busy.
We do. We try and spin a model about every other week. So 1 week we'll build the model, and that's really what the time-consuming thing is putting the instrumentation in the models, building all the pieces that hold things and move things, getting the motors right, getting the pumps right, getting the computers right, loading the model, and then we test usually in the following week, and then unloading and cleaning and starting the process all over.
Right.
Everything is, everything has to be G-loaded. Everything has to be G-load rated. So when you think about a pump, well, a pump usually has an impeller that spins. That has to be put a certain direction on the centrifuge, because if you put it one way, the G-loading is going to stop that pump from working. So we have to be really creative in how we build these models and making sure that everything is almost oversized. Everything I build doesn't usually work at 1G. So if I sit it right here on the ground, it's not going to work very well because it's overpowered for normal gravity. But it's made for putting it up in the centrifuge and spinning. And even things like computers you have to think about. Computers have fans and spinning hard drives. I can't have any of that on the centrifuge. So I have to look at very special computers and cabling and all the et cetera, so to make sure it can withstand the kind of G-loading that we put it under.
Right. Because you don't normally just know that off the top of your head.
No,
right?
and that's where for me the fun is, and that's where the experience and the expertise comes in with me and my team. We can't just put anything on the centrifuge. You have to really think through the problem.
Exactly. I understand that the centrifuge simulates very different environments and conditions, such as earthquakes, blasts, and floods. Can you tell us how that works and what you learned from those simulations? And we've already dived into that a little bit.
We have. The centrifuge is great because, again, I can scale everything down. What I do is I take the geometry of something. So if it's a levee, as we were talking about a second ago, I will scale that down to something that can fit within the centrifuge, and my platform is 1.5 meters by 1.5 meters by 2 meters tall. So that kind of gives you a sense of the box that I can put on the centrifuge and the size of the model that goes in that box. So I'll scale it down to something that fits within that box. And then when we scale it down, so if we scale it down by a factor of 20, that means that we'll usually spin at 20G. What that does is that gives us the same, when I spin it up to 20G, that gives it the same stress state as if it were full size. So you'll see a lot of researchers at ERDC scale things down. It just makes things more convenient. You can't test a 5-meter tall levee. It's too much soil, too much water. So researchers will scale it down, let's say even by a quarter. So now you're looking at maybe 1.5 meter tall levee. That's still a lot of water and a lot of soil for a researcher to have to manage and get data from. If I scale it down, say by 25, now that levee is only 200 mil tall. It's a lot easier to manage, a lot easier to do repeat experiments. And so that goes along with whether we're doing water experiments, we're doing anything with levees, dams, offshore sort of applications, and also earthquakes. So we're very fortunate we have an earthquake shake table that fits on the centrifuge. So we have another shake table at ERDC, but this is one that actually fits on the centrifuge. We bolt it onto the platform.
I was just going to say, how does it sit there?
It sits there. It bolts onto the platform. We have various accumulators that control the pressure of the servo actuators. And as we spin up, obviously the soil gets the loading that it would normally have in real life, and then we shake it. So it's literally spinning around the room, shaking on the platform. And it's one of the only ways we can do liquefaction studies, because liquefaction really relies on the soil being under the right stress and then shaking the soil or increasing the pressure in that soil from the shake that causes the pressure to push those soil grains apart, and we see liquefaction. So really, you could do liquefaction studies on 1G, but you need that stress in order for it to really happen. And so
stress is important.
Stress is important.
Okay.
Yeah.
So what are some of the benefits and challenges of using the centrifuge for research and development?
Certainly the benefits is being able to simulate those long-term behaviors in a short amount of time. You go back to the earthquake example. We're not standing around waiting for an earthquake. We never know when it's going to happen.
Right.
I can control that. I can say, hey, I'm going to push the button. Here's an earthquake.
Right.
There are things like consolidation of clays, long-term consolidations of clays, which has been especially important in London as we've built various tunneling lines and things through London. How does that clay behave if we tunnel through it? There are, that takes a lot of time for the consolidation of that clay. I can do that in days in the centrifuge. Take a slurry and go it all the way down to a fairly normally consolidated or even over-consolidated clay. So long-term behaviors in a short time frame, understanding those real-world problems with, again, those economically scaled models just makes it easier for researchers. We can increase the amount of usable data. Certainly, there is value, tons of value in numerical modeling, in monitoring, full-scale monitoring, full-scale experiments. There's tons of value in that, but they're very, with the numerical modeling example, you need validation. You need to compare it to something real. And that is where I can come in and be of value to those individuals and also do that full-scale modeling. Can we repeat this in an experiment and then change the variables? What if we add this new material? Will that help mitigate such and such disaster, et cetera? So that's another thing that I think is really powerful about the centrifuge. And then it's just, it's cost effective. I can get a lot of data in a short amount of time and then get that turned over and we can do something with it. And so those would, I say, the benefits. I think you said the challenges. I think, again, the challenges are it can be a challenging environment to work in only because you have to think about the mechanics of the experiment. Right. What direction do things need to go, the mechanical bits of the experiment. The instrumentation has to be miniaturized. That always brings an electronics issue that is difficult. And also you have to think about, no experiment is perfect. I can't replicate exactly Hurricane Katrina and everything that happened, but it's being strategic about what pieces are we really looking at and taking those key pieces and putting that into the experiment. If it was the loading of the wall, so increasing the water and decreasing the water on that wall, that's the part I have to replicate. So it's just understanding the problem and being able to replicate. And that's where ERDC researchers are really invaluable to me, because my job is to build the experiment, to design the experiment to survive on a centrifuge. I don't always necessarily know about the problem that's being brought to the facility. Right. And so that's where I love partnering with ERDC researchers because they know their problem. Right. They know what they're looking for. I'm just the person that tries to replicate it on the centrifuge.
And give them a good answer.
And give them good answer and good data. And that's, for me, that's one of the things I really love about this job is it's not rinse and repeat. Every day is a new challenge. Every day is a new problem. And it's not necessarily my problem. It's another researcher's problem. Right. But I get to figure out how to make it happen on a big spinning machine. And that's awesome.
Well, and the thing is how many people are on your team that make this researcher, get these answers that they need?
There's only 4 of us. Myself.
4?
There's only 4 of us. Yeah. There's myself. We have Joelle Westcott, who's just coming to us from CU Boulder. Just graduated with her master's degree, and again, CU Boulder has a centrifuge, so I'm very fortunate to have her. Mm-hmm. And then we've got Clint Barella. He's our lead technician. He's got over 20 years of ERDC experience. Mm-hmm. And then we've just recently brought in, he's only been here about a year, Ryan Bachman. Mm-hmm. He comes to us from the construction trades, but just having that knowledge of how to build things and make things survive in that environment is amazing. And we all work together great, and we all love figuring out these fiddly little issues of how to make a model work in the centrifuge, and it's great. So only 4 of us.
Sounds like a great team, though.
We have a good time. We do have a really good time.
Awesome. So the ERDC Centrifuge recently underwent some innovative upgrades. Can you tell us about these enhancements and what they mean for your research?
Yeah, the centrifuge was due, like I said, it was built in 1995. It was in about, the end of 2017, 2018. It was really in need of repairs. It had hit its 25, 30-year lifespan. And, every machine, if you think about your car needs repairs after a certain point. And the centrifuge was at that point. So we really went back to the drawing board about what we wanted and needed from this centrifuge. And I have to give credit to Chris Price, our branch chief, who really advocated for this overhaul. Mm-hmm. So we think about, there's two facilities associated with the Centrifuge Research Complex. There is the control facility where we control the centrifuge from, and that's also where our offices are. And then there's the containment facility which contains the centrifuge. This centrifuge has so much potential energy when it's spinning, so much mass, so much, it has to be in a separate building, and it's actually buried underground for safety reasons as well. Mm-hmm. So two separate buildings. So in the first building, the control facility, it was really outdated, so we essentially tore it down to the ground and rebuilt a functional facility. Some of the additions to that was that it's entirely fiber optic enabled. It's the first facility at ERDC to be so. So I can control the centrifuge from the office. It's from my office if I wanted to, but we also have a really super cool control room. We went NASA style, lots of TVs, and made everything really visually appealing. Mm-hmm. So that was kind of the control building. In the containment facility, now that's where the real magic kind of changed. The centrifuge itself really wasn't touched. We painted it because it needed it. But the nuts and bolts of the system, we didn't change. But basically every other mechanical, electrical, fluid, and data acquisition system was completely replaced. So we have a brand new DAC. I have over 180 channels of acquisition for researchers to use. Mm-hmm. We have all new camera systems, including a high-speed camera that works on fiber optics and a stereo camera. And again, the value of the fiber optics is that I'm able to transfer data from one building to the other very quickly. In fact, it's 40 gigabytes per second is how fast I can transfer the data that's coming off the centrifuge to us in the control room. That allows us to make decisions in real time about what's going on with the experiment and what we're seeing and controlling. And that, for me, is really exciting. You don't have to wait for all the pictures to upload. You can see them right there as they come in. And then just being able to upgrade all the channels of information that flow between the centrifuge and the control room. That's all now fiber optic enabled, which is, again, just increases that speed and capability. And then thinking what else? Oh, all the electronics, the motor control units were replaced, couplings on the motors were replaced for safety. We upgraded the hydraulic systems, and the earthquake shaker also got a huge overhaul. So that is now completely redone as well.
Sounds great. You really got some enhancements.
It was fabulous. I think it was a blessing and a curse. We started in late 2019, the construction, and so what's coming. We all
know what happened.
Yeah, you know what's coming.
You don't even have to say it.
No, yep. So March 2020, we were shut down.
Right.
But we couldn't stop for that long, and so the three of us, the two technicians and myself, we were back at ERDC by May, and we were the only three in the building just getting that facility ready. And it gave us an extra year because, again, the people who had to fix the centrifuge were coming from France, so that took another year to get them over. I say I lost the best advertisement I ever could have had was because that building came down and come back up, and everyone would have seen it, but no one saw it because no one was on station.
It was like a ghost town.
It was a ghost town. It was. It was just the three of us, we felt like. But
right.
That gave us an extra year to actually be as picky as we wanted to be and really question every bolt and every wire. Is this what we want? And in the end, we changed a few things that we had originally thought, yeah, this is going to be perfect. And we went back to the drawing boards a few times, but it was nice to have that extra time.
Awesome. So this year, we're celebrating how the labs came together 25 years ago to form one ERDC, one organization of experts across multiple disciplines. How do you collaborate with other laboratories or organizations that use the centrifuge or its data?
So the other laboratories, incredible. I know we're located with GSL, but we consider ourselves to be an ERDC asset because every lab could utilize the centrifuge in fun and unique ways. I think about EL, and I think about the current problem with PFAS and chemical plumes and oil spills and spills. That's a stress problem. That liquid needs, migrates into the soil. It seeps into the soil, and what you'll have is a huge plume, and that's a time problem. How long, and with given time, how big is that plume going to get? Where is that plume going to go? You have a clay liner over here. Is that going to move the plume in one direction or another? that's a centrifuge problem in my mind, because that's a stress problem. You let that liquid go, and with time you see where it seeps, and we can recreate those boundary conditions within the centrifuge and watch that faster than what we would see in real life. So now I've taken a 50-year problem and scaled it down to a day. And so when I think about some of the things happening at Yale, that's one of the problems I think about. Certainly military engineering. We think about military engineering and some of the blast mitigation problems and looking at force protection. We can do blasting in this centrifuge. In fact, it was made for that. Another reason why it's buried underground. One of the projects we looked at many years ago, I think 2005, following the Oklahoma City bombings, we were looking at progressive collapse of facilities and how far into a building, if one part of a building goes down, how far into a building does the building go down? Mm-hmm. And you saw this, recently, 2-something years ago in Miami, the apartments mm-hmm. that, the Oceanside apartments, that's what they were called, that came down. Again, the bottom of the building came out and the building progressively collapsed. Mm-hmm. Where that stopped is still sort of a bit of a mystery in all these kinds of cases. And so we were examining that in the centrifuge. So to think of a structural, potentially military applications sort of problem. Mm-hmm. And then we have lots of university partners that we're working with. We're working with the University of Mississippi right now, working with the University of Oklahoma. They all have great, unique problems that we love to investigate. And again, there's only 4 of these centrifuges in the U.S., so it's nice to partner with those universities so they can have access to this kind of this tool.
So valuable. It's great. And such a learning tool.
And it's fun to have the students come too, because right. We've got the space for them. They just join our team and jump right in and start building the models. It's great. It's real hands-on, and it's fun for them and it's fun for us.
They get to make something go really fast.
They do. Kind of nerve-wracking that first time.
I'm sure.
Still nerve-wracking.
I'm sure.
It is.
So what are some of the future plans or goals for the centrifuge and its research?
I think expanding its research portfolio is one of my major goals. We've done a lot with USACE infrastructure, a lot of civil infrastructure. I think there is certainly much more to do with that. And certainly I think where the real change can be is there's probably not an experiment that hasn't been done, but what hasn't been done is there's incredible capabilities with cameras nowadays, between high-speed cameras and stereo cameras, which look 3D at a problem.
I was going to say, what is a stereo camera?
A stereo camera has 2 lenses like your eyes, mm-hmm. and because it has 2 lenses, the camera can see depth. And so we are able to see, for instance, a levee, water overtopping a levee. We can watch the head cut into that levee, and I can tell you exactly how deep that cut is going, how wide that cut is going. And I just take what is essentially comes back to me as a point cloud of an X, Y, and Z, so a location and a depth, and I'm able to tell with time exactly how deep that cut is going. With a camera, I've never touched the soil. I don't have any measurements on the soil. I'm simply looking at it and recording that data. So we've got that capability. Certainly lots to do with lasers. There's just so many fundamentally very new and very cool instrumentation and camera developments, and it's happening every day. There's something new on the market that I love incorporating into centrifuge research. And now, because of the fiber optics and the upgraded capabilities, I'm able to incorporate these things really fast and see, hey, is this something that could be really neat for the centrifuge that no one else is doing? So and then just reapply to some experiment that's already been done. I think that's really where the fun for me of the centrifuge is incorporating all these new technological advances into our testing mechanisms and testing capabilities. And I think my other goal is really growing that partnership with universities that don't have access to the centrifuge and what it can do. There's just certainly a lot of research being done out there, a lot of experimentalists trying to do things with big 1G models that, if they wanted more data, certainly come to us. We can miniaturize it and help you expand that profile, and that's great for me. That's a lot of fun.
How do people out there that need to have an experiment like this done, how do they know that ERDC is there to do that type of?
Well, I mean, this podcast is a great example.
There you go.
No, I mean, just getting the word out there that we
right.
even have these capabilities. We have these partnerships. We have partnerships with universities all over the U.S. and all over the world, really. I'm starting a new project with Oxford University. It's, I think getting the word out there that ERDC exists, we have incredible capabilities. I'm a centrifuge, but I'm right next to a plume from CHL, and I'm right next to an environmental lab, and we've got the supercomputer. We have all these resources in one location we can bring together to facilitate this kind of research in whatever you want to investigate. So I think, one, knowing that it exists, and two, knowing that ERDC is hungry and happy for partnerships.
Right.
We have the capability. We have a lot of resources to either support people that are wanting to do this research, or researchers coming to us who have the support but just need the facilities. I think that we have a lot of capability, and it's just getting the word out that it exists.
Right.
So yeah, if there's anyone out there that's really interested in centrifuge research, I'm here, I'm ready. Let's go, let's spin it. That's my job.
Let's spin it. I like that. That's a good hashtag.
I like it.
Let's spin it. Okay. And the thing is, ERDC is such a cool place. I think ERDC keeping it cool, because that's what we do. Just like you said, all the cool things that go on there, it's mind-blowing. It really is.
And you think about the people here. I mean, the mind power of ERDC, and not even, now we've talked about the facilities, of course, because that's what I love, but the mind power, the amazing researchers we have here who have so much experience across the United States, across the world, experts in their field. It's not hard to, throw a stone and say, hey, what do you got? What idea do you got? Can that combine with this idea? The environment itself is incredible to work in.
Exactly. And again, I can tell you have fun.
It is. It's fun. Yeah, it is fun.
All right. So we're going to dive into closing out with our last question. What would you like listeners to learn from this valuable conversation?
Yikes. I think what we just said is really what I would like them to learn, is that I don't think I've met anyone at ERDC who doesn't have incredible passion for the research that they do. Whatever it is, whether it's, I could think tree rings or the levees, or looking at the CHL models, they are passionate about finding a way to get the answer in a scientific, reproducible, validation capable experiments. And I think that's what I would love to say. One, thank you for the passion that I talk with everyone with, and and experience at ERDC is fantastic, but that it's a great place to work, and the centrifuge is there to support all of them. That's what we're here for. We don't do our own little centrifuge research. We really rely on the passions and the experience and the knowledge and the needs of not only USACE and other organizations, but also the researchers at ERDC to bring us those good ideas and want to use us. So we're here, and that's what we want to do.
Fantastic.
The U.S. Army Engineer Research and Development Center, or ERDC, is the premier research and development center for the U.S. Army Corps of Engineers. Hello, I'm Carol Coleman, and I would like to share with you how ERDC makes the difference. Established in 1998, the ERDC is home to more than $1 billion worth of world-class facilities located in 7 laboratories and multiple field sites across the country. The organization's main campus is situated on the historic Waterways Experiment Station in Vicksburg, Mississippi, and consists of the Coastal Hydraulics Laboratory, the Environmental Laboratory, the Geotechnical and Structures Laboratory, and the Information Technology Laboratory. ERDC also operates 3 laboratories not located on the West Campus, including the Construction Engineering Research Laboratory in Champaign, Illinois, the Cold Regions Research and Engineering Laboratory in Hanover, New Hampshire, and the Geospatial Research Laboratory in Alexandria, Virginia. Each laboratory has their own unique mission and operates as integrated teams of engineers and scientists to address a broad range of science and technology issues. The Coastal and Hydraulics Laboratory, or CHL, addresses an entire spectrum of water resource challenges. Their mission is to deliver solutions to our nation's most challenging coastal and hydraulics problems. As part of the CHL, the Field Research Facility, or FRF, is a U.S. Army Corps of Engineers field site located in Duck, North Carolina. The cornerstone of the FRF's contribution to coastal research has been its long-term data measurements that stretch back to 1977. The long-term measurements have made the property one of the best studied beaches in the world. Providing solutions for tomorrow's environmental challenges, the Environmental Laboratory, or EL, is ERDC's primary center for ecosystem science, ecosystem technology, and environmental resiliency research. The laboratory is home to the Aquatic and Wetlands Ecosystem Research and Development Center and the Hazardous Waste Research Center. ERDC's Geotechnical and Structures Laboratory, or GSL, supports our nation's defense, security, public safety, and infrastructure. GSL is home to the world's largest heavy vehicle simulator, the Centrifuge Research Facility, and the Advanced Blast Load Simulator. In today's fast-paced digital environment, the Information Technology Laboratory, or ITL, provides innovative solutions to solve the nation's most complex and challenging IT and computational issues. The laboratory's Supercomputing Resource Center is one of only 5 Department of Defense computing centers operated by the DoD High Performance Computing Modernization Program. For more than 50 years, ERDC's Construction Engineering Research Laboratory, or CERL, has supported the Army's ability to design, build, operate, and maintain its installations and contingency bases. Located in Champaign, Illinois, the laboratory is home to the Triaxial Earthquake and Shock Simulator. ERDC's Cold Regions Research and Engineering Laboratory, or CREL, delivers environmentally relevant and transformative engineering solutions to test, evaluate, and improve infrastructure and equipment, particularly for use in cold regions. Located in Hanover, New Hampshire, the laboratory is home to the Frost Effects Research Facility, the largest refrigerated warehouse in the United States. The Permafrost Tunnel Research Facility is a U.S. Army Corps of Engineers field site operated and maintained by ERDC's CREL. The tunnel, located just outside Fairbanks, Alaska, is a unique natural research facility with features up to 40,000 years old. ERDC's Geospatial Research Laboratory, or GRL, located in Alexandria, Virginia, serves as the Geospatial Research and Development Laboratory of the U.S. Army Corps of Engineers. GRL is the only dedicated geospatial research and development laboratory in the entire Department of Defense. As the premier research and development center for the U.S. Army Corps of Engineers, ERDC has unique, world-class equipment and facilities. To learn more how ERDC discovers, develops, and delivers innovative solutions to the nation's toughest challenges, be sure to listen to Beyond the Gates on News Talk FM 107.7 on Thursdays at 8:15 a.m. and 9:10 a.m. or check out past shows on vicksburgradio.com. We discuss exciting research with representatives from one of the 7 ERDC laboratories, and they describe how their projects are important to the community, the region, and the nation. Again, I'm Carol Coleman with ERDC. Thanks for listening.